Hey everyone, just wanted to do a quick introduction to equilibrium, which is a pretty substantial unit in grade 12 chemistry. So it is very important to understand the fundamentals of equilibrium. So the core idea is that up until now in chemistry, you've really just been thinking about reactions going one way. So if we think of the synthesis of water, we have hydrogen and oxygen gas combining to give us water. And I'm just going to do the appropriate mole ratios here. So we need a 2 here and a 2 here to make it balanced. So this equation just tells us that the reaction can go one way. And that's fair. We have reactants, they're going to give us products. And, we're not going to see a situation where water is going to, spontaneously break down and give us hydrogen and oxygen. So this is a one-way reaction. However, some reactions are reversible, and that is denoted with this strange-looking arrow. It's an arrow pointing forwards and backwards. So in this example here, we have nitrogen gas and hydrogen gas reacting to give us ammonia. But what can also happen is the ammonia can go back and break down into nitrogen and hydrogen. So this means that the reaction is reversible and we can have a forward and a backward reaction. However, the reaction will eventually reach equilibrium, meaning the rate of the reaction going forward will equal the rate of the reaction going backwards, and we will have stable concentrations of both our reactants and products. And a way we can represent these equilibrium concentrations is with something that's called an equilibrium constant. And usually that's referred to as the K value of an equation, a chemical equation. And the way we can represent K is we can equal it to the concentration of our products over the concentration of our reactants. And since we're dealing with concentration, if we had a solid in this reaction, we wouldn't actually consider it in this equation because solids don't have a concentration. The same would be true if we were dealing with partial pressures. Sometimes equilibrium questions will deal with partial pressures. I prefer to work in concentration, but it's always going to be some sort of mole ratio that you need to deal with. And speaking of mole ratios, we need to make sure our equation is balanced. So I need 2 nitrogens over here, and in order to balance the hydrogens, I would need 3 here. So we have our equilibrium concentrations here, but our mole ratios also need to be represented in this equation. So whatever coefficient we have in front of our products or reactants is actually going to be an exponent. So we have a 2 for NH3, and we have a 3 for H2. So what does the value of K actually tell us? If the value of K is greater than 1, then the reaction is heavily favored to the right. That doesn't mean that there isn't going to be a little bit of a reverse reaction happening, but it's heavily favored to the right. Most of it is going to the right. And so, conversely, if K is less than 1, the reaction is favored to the left. But let's say we already are at equilibrium. So let's say we have this example and we've let the reaction happen. We've now reached equilibrium concentrations and everything is stable. If I cause a change to the system, the system is going to want to fight back against that change. So for example, let's say I remove some nitrogen gas. Since I've removed a reactant, the shift will be to the left to try and create more nitrogen that we've lost, the nitrogen that we've lost. And that would be the same case if we were to remove hydrogen. We're going to see ammonia gas break down and give us more hydrogen. Same logic applies if we were to remove ammonia. We've lost some product, so the system wants to create more product. And this one's a little different. Let's say we increase the pressure. So let's say this reaction is occurring, in a container of a certain pressure, and we were to increase the pressure. What's going to happen is the system wants to decrease the pressure as a response to that. And the way it can do that is by creating more ammonia. Because we have one gas on our product side and two gases on our reactant side. So if we create more product, we're effectively going to decrease the pressure. So this is a lot of theory, a lot of conceptual thinking. Let's get to a question that uses some real numbers. And I'm actually going to just add a bit more information here so we can solve this question. So, question number 1. What are the equilibrium concentrations for the following reaction? So we have hydrogen and iodine gas giving us hydrogen iodide. First things first, let's balance our equation. I just need a 2 here. So we have a 2-to-1 mole ratio between our product and our reactants. We've also got a K value to work with. But all I have here are the initial concentrations, that's I, of our reactants. I don't have equilibrium concentrations, so I can't set up my K equation just yet. I need a way to represent my equilibrium. So this is our initial values. We have 0.35 molar of hydrogen and iodine and 0 of our product. So based on our mole ratios, we can think of how these concentrations are going to change. We're going to see a decrease in concentration for hydrogen and iodine, represented as a subtraction of X. And X is referring to our mole ratios, right? So for every 1 mole of hydrogen and iodine that are reacting, we're going to get 2 moles of hydrogen iodide. So here we could say we're gaining 2x of our product, but we're only losing 1x of our reactant. And that's all due to our mole ratios. So if I want to represent my final values or my equilibrium values, I can just take my initial value and connect it to my change. So we have 0.35 minus x, and here we're going to have just our 2x. So now we can set up our equilibrium equation, or our K equation. So hydrogen iodide, our equilibrium concentration is represented by 2x, and we need to put that to the power of 2 because of our mole ratios. And then down here, we have 0.35 minus x times 0.35 minus x. We also have our K value. So let me write this out again. Since we have 2 of the same values here, you can also represent that as 0.35 minus x squared. So it's looking a little tricky to isolate for x here, but we can do a bit of math to make this easier. Since I'm squaring both my top and my bottom value, I could rewrite this as 2x over 0.35 minus x to the power of 2. So I've just taken out the 2 and applied it on the entire fraction. How do we get rid of a power of 2? We can square root both sides. So let's move over here. And now I have square root 45 equals 2x over 0.35 minus x. Now I'm just going to quickly run through this to isolate for x. Really, this is just, grade 10, grade 11 math review. So hopefully you're feeling okay on that. So we just need to isolate for x. We're going to move our x components all onto one side. And finally, we can solve for x. And our value is approximately 0.27. So, great. We have our change in our concentrations, but that is not the equilibrium concentrations. For that, we need to plug this value into all three of our equilibrium terms. So 0.35 minus 0.27 is going to give us 0.08. And that would be the answer for both hydrogen and iodide. And then for hydrogen iodide, we just need to multiply that by 2, which will give us, 54. Okay. Or sorry, 0.54 molar. So that would be our equilibrium concentrations. Okay, that's really the basics of equilibrium, but things can get a bit more complicated. So let's try this question down here. Calculate the equilibrium concentrations for the following reaction. There is 0.5 moles of CO2 in a 2-liter tank, and the equilibrium constant is 6 times 10 to the negative 7. So right off the bat, we've been given a K value, and we've also been given the number of moles of our reactant. But we want to work in concentration, so we have 0.5 moles in a 2-liter tank. So to find our concentration, we need to divide moles by our liters, and that is going to be 0.25 molar. Okay, now we can set up our table. And this is the same as the previous example. We have our initial values, our change, and our equilibrium. This is often referred to as an ICE table. So we know our initial concentration of CO2, and we start with 0 product, carbon monoxide or oxygen. Remember, we need to balance our equation first for mole ratios. So we would need to add a bit more oxygen onto this side and then balance that out with carbon monoxide. All right. So we are going to see a 2x decrease in CO2 because of our molar ratios. We are going to see a 2x increase for carbon monoxide, again, because of the molar ratios. And oxygen is a 2-to-1 mole ratio, so that will only be a plus x. So we want to represent our equilibrium. We can do that like so. And now we have a complete ICE table. But let's set up our k equation. So our products are going to be 2x to the power of 2 times x, because that is our CO and O2 concentrations. And then we have 0.25 minus 2x squared. Again, because of mole ratios. This is also 6 times 10 to the negative 7. Now this one looks a little bit trickier to solve because we can't really remove the exponents. However, what we can do is use something called the rule of 100. And this is very useful. So what we're going to do is we're going to take our initial concentration, which was 0.25 molar, and we are going to divide it by our K value. And if this ratio is greater than 100, we can ignore the change to the concentration. So if you plug this into your calculator, you'll know that it's much larger than 100. And what that means is the change in our initial concentration is going to be so small, we can effectively ignore it. And that's going to make this a lot simpler to solve. So I can just cross out my 2x in the bottom, and now I would simply solve for my x value. So we have it's 2 being applied to both terms here. That's going to give me a 4x squared times x over 0.25 squared, which will be 0.0625. And again, all we need to do now is solve for x. Just some basic math. So we're going to move this onto this side. That gives us 3.75 times 10 to the negative 8 equals 4x cubed. Divide out our 4. That leaves us with 9.375 times 10 to the negative 9 equals x cubed. How do we get rid of this? We need to cube root both sides. And x is approximately 2.11 times 10 to the negative 3. So we have our x value. And so to get our equilibrium concentrations, all we would need to do is take this value and plug it in to here. So the rule of 100 is very useful to make your equilibrium equation a lot simpler. All right, one more to go. Hopefully this one will go pretty smoothly now. Solve for x given the following ice table. So we have the same equation from question 1. This is hydrogen and iodine reacting to give us hydrogen iodide. We already have our ice table set up, so that's great. So all we need to do is set up our equation. So we have 2x to the power of 2 over 0.3 minus x times 0.2 minus x. Now, this is the trickiest setup so far. Why? Because we can't do any mathematical tricks to make this easier. We can't get rid of the squared like we did up here because we don't have the same exponent on the bottom. And we also can't follow the rule of 100 because if I take either 0.3 or 0.2 and divide it by 45, neither of these follow the rule of 100. So we can't do that. Unfortunately, what we are going to have to do is expand everything here and set up a quadratic. So I will spare you that. hopefully you can do that on your own. If not, there's tons of great videos online going over the quadratic equation. But basically, if we expanded everything out and set up a quadratic equal to 0, we would get this wonderful equation. Whoops, not a great circle there. Let's try that again. Okay. And we need our trusty quadratic formula to solve for x, because there is no way we are going to factor this on our own. So we have our a value here, we have our b value here, we have our c value here. And I will fast forward through all of this and just let you know that the two x values that you can get are 0.18 or 0.37. Right, and we are going to get two answers because we have a plus minus in front of the square root. So there are two possible values for x. However, logically, only one of these is going to work, right? We started with 0.2 molar of iodine. So if I have a change of 0.37, that's impossible, right? I'm going to have a negative concentration for my reactants. So we can ignore this one. The only one that makes logical sense is 0.18. So this is our final answer. So really what I want you to understand is how to set up your equilibrium equation and then all the tricks you can use to solve for x. If you can get rid of it mathematically, or not get rid of it, you can simplify it mathematically by removing the power of 2 and thus getting rid of it being a quadratic. If that's no good, you could also follow the rule of 100. And I think I wrote that back here. Yep, so in this question we could use the rule of 100 to simplify. But if you've tried all of that and you're still stuck, we are going to have to go back to the trusty quadratic equation. So I hope that was helpful. There is a fairly large unit on this in grade 12 chem, so very important to get your fundamentals down for equilibrium. Thanks for watching, and happy studying.